Every Python developer hits the same wall on day 3. You've probably tried to speed up your Python code using threads, only to find it got slower, or at best, no faster, even on a multi-core CPU. You import the threading module, you spin up worker threads, you watch your CPU utilization, and nothing. The cores sit idle, or your program just crawls. I want to show you now exactly why that happens. This isn't a bug in your code, or a flaw in the threading module itself. It's a fundamental design choice within the most common Python implementation, CPython, and it's called the Global Interpreter Lock, or GIL. Understanding the GIL and the entire execution model that surrounds it is crucial for writing efficient Python, especially when you start dealing with concurrency or performance-critical applications. Today, we're going to pull back the curtain on Python's internals. First, you'll learn to differentiate CPython, the standard Python you download, from alternative implementations like PyPy, understanding their core mechanisms and the performance trade-offs each one makes. This is not just trivia, it dictates how your code actually runs. Then, we'll trace the complete execution flow of a .py file, from the moment you hit enter on your terminal, through its compilation into bytecode, and finally, its execution by the Python virtual machine. We'll also uncover the purpose of the mysterious .py cache directory that sometimes appears in your project folders. Finally, we'll tackle the global interpreter lock head-on. You'll understand its purpose, its impact on CPU-bound multi-threaded Python applications, and why it's both a blessing and a curse. By the end, you'll also identify the key domains where Python truly excels, not despite, but often because of, its unique design philosophy. When I first started, I thought Python was just Python. One language, one way it runs. But that's not quite right. Python, at its heart, is a specification, a set of rules for how the language should behave. CPython is the reference implementation, the one you get from python.org. Think of it like the official blueprint for a car, and CPython is the factory model built exactly to those specs, using C as its construction material. CPython compiles your Python source code into an intermediate representation called bytecode. This bytecode is then executed by a stack-based Python virtual machine. This design choice simplifies memory management significantly, as CPython can rely on C's well-understood memory model. It also means that many performance-critical parts of CPython are written in highly optimized C code. But CPython isn't the only game in town. There's PyPy, for instance. If CPython is the standard factory car, PyPy is like a custom-built race car. It also implements the Python specification, but it uses a just-in-time, or JIT, compiler. Instead of interpreting bytecode instruction by instruction, PyPy analyzes frequently executed code paths at runtime and compiles them directly into highly optimized machine code. This JIT compilation often leads to dramatic performance gains for long-running, CPU-bound programs. I've seen PyPy make some applications run 10 times faster, sometimes even more. The trade-off, however, is that PyPy might have limited compatibility with certain C extensions, especially those that directly manipulate Python's internal structures. You also have Python for the JVM, IronPython for .NET, and MicroPython for embedded systems, each with their own specific platform benefits. Now that you understand the different flavors of Python, the execution model is going to make perfect sense. Python isn't purely interpreted like a shell script, nor is it purely compiled like a C program. It's a hybrid. When you run a .py file, say one named myscript.py, the CPython interpreter first takes that human-readable source code and compiles it into bytecode. This bytecode is a low-level, platform-independent representation of your Python code. Think of it as a set of instructions for a hypothetical CPU, specifically the Python virtual machine, or PVM. It's similar to how Java compiles source code into JVM bytecode. The key difference is that Python's compilation step happens automatically and is largely invisible to you. Once the bytecode is generated, the Python virtual machine takes over. The PVM is a stack-based interpreter that reads and executes these bytecode instructions one by one. There's no separate linking step like you'd find in C or C++. The PVM handles everything, from allocating memory for objects to managing the call stack for functions. This entire process is what we mean when we say Python is an interpreted language. Here's where it gets interesting. This compiled bytecode isn't just ephemeral, it's often saved. When you import a module or run a script, CPython stores this bytecode in files with a .pyc extension inside a special directory named .py cache. For example, if you have a file mymodule.py, you might find mymodule.python-39.pyc in .py cache. These .pyc files act as a cache. The next time you run your script or import that module, Python checks if the original .py source file has changed. If it hasn't, Python skips the compilation step and loads the precompiled bytecode directly from the .pyc file. This significantly speeds up subsequent imports and program startup times, especially for larger projects with many modules. You can actually peek into this bytecode yourself using Python's built-in dis module. Let's define a simple function, say add, that takes 2 arguments and returns their sum. Alright, define add, with arguments a comma b, colon, return a plus b. This is standard Python syntax. Now, to see the bytecode, you call import dis and then dis.dis with argument add. What you get back is a list of low-level instructions that the PVM will execute. For our add function, you'd see something like load fast 0, load fast 1, b, binary add, and return value. The load fast instructions push the values of a and b onto the PVM stack. Binary add pops those 2 values, adds them, and pushes the result back onto the stack. Finally, return value pops the top of the stack and returns it as the function's result. This output shows you the granular steps the PVM performs, far removed from the high-level Python you wrote. This is the part most tutorials skip, and it's the answer to our initial paradox. The Global Interpreter Lock, or GIL, is a mutex, a lock, inside CPython that protects access to Python objects. Its purpose is to prevent multiple native threads from executing Python bytecode simultaneously. Think of it like a single-lane bridge. Even if you have many cars or threads trying to cross, only one can be on the bridge at any given moment. The GIL exists primarily to simplify Python's memory management. Python objects have reference counts, which determine when memory can be deallocated. Without the GIL, multiple threads could try to modify these reference counts simultaneously, leading to race conditions and memory corruption. The GIL ensures that only one thread can modify Python object state at a time, making Python's internal C code much safer and easier to develop. The impact of the GIL is profound for CPU-bound applications. If your Python code spends most of its time crunching numbers, like calculating prime numbers or performing complex mathematical operations, adding more threads will not speed it up. In fact, it often makes it slower due to the overhead of context switching between threads and the contention for acquiring the GIL. However, the GIL releases its hold during I/O operations, such as reading from a file, making a network request, or waiting for a database query. This means that for I/O-bound tasks, Python threads can still provide concurrency benefits. While one thread is waiting for an I/O operation to complete, another thread can acquire the GIL and execute Python bytecode. This is why you might see speedups for network-heavy applications even with the GIL in place. Given these design choices, you might wonder where Python truly shines. Python was designed to optimize developer time, not raw execution speed. Its extensive standard library and rich ecosystem allow you to accomplish complex tasks with minimal code. This philosophy makes it the de facto standard in data science and machine learning, with libraries like NumPy, Pandas, TensorFlow, and PyTorch. It's also a powerhouse in web development, powering frameworks like Django, Flask, and FastAPI for everything from small APIs to large-scale web applications. For scripting and automation, Python excels at system administration, file manipulation, and acting as glue code between different systems. Its clean syntax also makes it the most common first programming language in universities, which is a testament to its ease of learning. So what have you learned today? You now understand that CPython is the standard Python implementation, but alternatives like PyPy offer significant performance gains through JIT compilation, albeit with potential compatibility trade-offs. You can trace a .py file's journey from source code to bytecode, executed by the Python virtual machine, and you know the dunderpy cache directory stores those compiled .pyc files for faster loading. Crucially, you now grasp the purpose and impact of the global interpreter lock. You know it prevents true parallel execution of CPU-bound Python threads in CPython, but it simplifies memory management and allows I/O-bound threads to still achieve concurrency. This knowledge will save you hours of debugging when you encounter unexpected performance in multi-threaded Python applications. Next time, we get our hands dirty with the actual building blocks of every program, setting up your Python development environment.